All right, so here we have a population that has a normal distribution. The mean is 181.9. The standard deviation of the population is 79.9. You intend to draw a random sample of size n equals 19. So right away, a flag goes off in my head and it says, oh, I have a group of people here. So that means I'm probably going to need the central limit theorem. Okay. So then I go on and read what they're asking of me. So find the probability that a single, single. So they're saying, forget about the group for a minute. So this is just the regular normal distribution. Okay. So let's do that one first. Screenshot. So just doing the top part. And new page. And again, this is number 14 in our current homework assignment. If you're looking at this way in the future, it could be different. Things change over time. So for the first question here, they're asking about a single person, not this group of 19 people. And if it's just a single person, then that's just a regular regular normal distribution. So for this distribution, I need to know the mean. So I'm going to draw a quick sketch of this one. So draw a rough normal shape, mark the middle. It says the middle should be 181.9. And then they're asking me about 196.6, which is somewhere out here. A standard deviation is almost 80. So one standard deviation would be about there, 2 would be about there, 3 would be about there. So one standard deviation is like 180 plus 80, which is like what, 260-ish is that number right there. So plus one standard deviation is about 260. And the reason I'm checking that is I'm trying to figure out where does 196 live according to that spread and that center. Okay. Do I have to draw the picture? No, it just kind of helps me wrap my brain around it. So that's like 180-ish. This is 260. So this number right here, 196, has got to be like over here-ish. So I think that's about where 196.6 lives, roughly. And so I want to know what's the probability of getting that number or lower. So that is a left tail, right? Because it has a less than, left for less. And that's going to be just a bit bigger than 50%. So I can guess the answer is bigger than 50%. And it's a left tail because it's a less than. So I'm just kind of roughing out the answer there with a picture. So then I have to bring up a normal distribution calculator, which could be StatKey, but it could be a spreadsheet. So I can whip out a spreadsheet to do this too in a sec. And I have notes on how to use a spreadsheet to do this. So whenever you use the normal distribution calculator, you got to set your parameters. And we were given a mean of 181.9, 181.9, and a standard deviation of 79.9. So make sure you get the right mean and standard deviation. And then, let's see, my zoom tools are in the way down there. We need to do a left tail because it was a less than probability, and we need to change the x value down here. And I think that was what, 196.6 for mine. Okay. And yeah, you can see that's a little past the center where I was guessing it was. And here they claim it's 57.3%, 0.573. And I thought it was a little bigger than 50%. So we're just kind of sketching it out and guess. And we've been doing these sketches, right? So we're just going to keep getting better at doing them. We're going to do them next week too, and the week after. All right, and it says enter an integer or a decimal. There's no percent symbol, so I'm assuming they want me to put the 0.573 here. All right, so that's it. That's the answer there. To do this in a spreadsheet is a little trickier. I think I'm going to skip that for now, actually, because we're getting close to the end of the hour. I have recordings on it. So let's do this one next. I need this given information in a new page, and then I need the question. Ooh. And now I'm just kind of come back to this page in a minute to note a couple different things. Add to current. In this case, let's see, find the probability that a sample of n equals 19, okay, so right away, flag, goes off, star, think central limit theorem. What does it mean to think the central limit theorem? Well, if you've read it all, any of chapter 7, section 1, the central limit theorem says for your standard deviation, use whatever they claim the population is, but divide by the square root of the sample size. That's the new standard deviation, okay? So for this right here, my mean is going to be the same as it was before, 181.9. But since I'm talking about a group of people, the central limit theorem kicks in and says, whoa, change the standard deviation. So the STD here is going to be whatever 79.9 is divided by the square root of 19. And I'm going to have to whip out a calculator to do that. So let me do that quick. Calculator. So 79.9 was the old standard deviation. Divide by the SQRT is square root of 19. And Google says 79 over the square root of 19 is about 18.33. All right. So this means I now have a new standard deviation of about 18.33. And other things to think about, we aren't looking at the score of an individual, but the mean. Anytime you see mean, that means use the central limit theorem. And notice they have an M here for mean, whereas in the first question they asked me, they had an X for an individual. So X is an individual value. Sometimes instead of M, they might write it like this. So I would have written it, what's the probability that the average of this group is less than 196.6? Because often M means median, but they're using it for mean here. All right, so the only way to do this is to whip out a calculator that does this kind of thing, where we tell it what is the mean, what is the standard deviation, and what score are we interested in. Again, this is a less than, so it's a left tail. If it was a greater than, it'd be a right tail. So less or left. Less is left. All right, find your calculator and adjust it. So I need to edit the parameters. I have the same mean, but now I have about 18.33. And you might ask, ooh, how do I round that number? I usually try to go some like 4 or 5 significant figures. So I have 4 right there. If I was really worried, I would just copy this whole number and stick it in there. But I don't think that's going to give me much of a different result. So you could double check by adding more decimals and see if the answer changes, but it probably won't. So I think that's good enough. All right, and then I need to plug in, that's a left tail test, and I want, again, a mean of 196.6. And now it says a slightly different probability because the standard deviation shrunk, right? Instead of being about 80, it's about 18. So that means if I take a number that's a little higher, that means I'm accumulating more stuff. So this time I get a probability of 78.9%. So the big thing is from now on, we got to think about, are we calculating something for an individual or for an average of individuals? If it's an average, we have to adjust the standard deviation. Otherwise, if it's a single person, we don't worry about it. And that's the big difference here. And I highly recommend you draw a sketch. And did I draw a sketch there? Oh, I'm such a bad student. I'm sorry. Sometimes I'm not a good student. Ask my wife about that. Okay, so I should have sketched this out. So rough sketch, what I usually do is I draw a bell shape. I mark the mean, 181.9. I then think about the number I have. Is it to the right or the left? It's to the right. So the question is how far to the right? So let's say that's about 1 standard deviation, 2 standard deviations, 3 standard deviations out there maybe. 1 is 18. Okay, so 18 is close to 20, 20 plus 180. So 1 standard deviation to the right is about 200-ish. So my 196 should be about just a little less than that. So maybe it's over here. In the previous example, we saw that if we were exactly 1 standard deviation, that's the 84th percentile. So I'm guessing that in my picture, this is greater than 50%, but less than 80%. Do you have to do those guesses all the time? No, but I try to kind of rough out the picture with at least one standard deviation marked to try and figure out where my number lies. So I'm guessing that my answer probability is somewhere between 80% and 50%. Now, it certainly helps that I already had the computer calculate it, right? So that was not a very good guess because I was cheating, sorry. All right, so let's see, let's do one more and then we'll call it quits for today. Getting asked about 18 and 19, and I can't remember if they're in this section. So again, as you click through the homework, you might get a new message pop up at the top. That means you should consider what I wrote there. So 15, 16, 17, okay. 18, all right. So 18 gets a little tweaky on us because now it says, all right, we're going to use a proportion instead of a mean and the standard deviation, the central limit theorem. Now, this is actually covered in 8.3, which is about confidence intervals, which we covered a while ago. You might have seen this formula in the book, but I had crossed it out, said, hey, we'll worry about this later. Well, we're worrying about it now. So let's copy this whole thing in. So we're reaching back to the future here. Let's grab all of it. And new page, please. Okay. So here, again, I'm thinking back to confidence intervals. And with confidence intervals, we had those pictures that we drew. That's where I started you in drawing these pictures. And with confidence intervals, it's the sample proportion that went in the middle. And then we looked out to either side to get an interval. In this case, it's the population proportion that goes in the middle. So anytime we're talking about proportions, we can use the central limit theorem most of the time. And there was a critical thinking question about this, like when we're allowed to make calculations on a proportion to do confidence intervals. And if you think about that, you might remember for a proportion confidence interval, if the number of successes is greater than 5, and the number of failures is greater than 5, and I had some kind of random sample, then I can follow through with this math. Random sample. So you may remember that critical thinking question from a while back, 2 weeks ago. So with proportions, the mean for a proportion is the proportion. So mu and p are the same thing for proportion. So I'm going to put p in the middle. And then the standard deviation for proportions, so mu for proportion, standard deviation for proportions, that's going to be this crazy square root. So it's the square root of p times q divided by n, if you write it out lengthwise. And q is the failures, the percent of failures. So just a note here, q is 1 minus p in terms of a percentage, because 1 is 100%. So they say, what's the mean of this distribution? The mean is the proportion, right? I say it right up top there. So let's see, they have the true proportion is 4.6%. So the mean is 4.6 or 46%. The mean is 0.46. And with proportions, we usually state them as decimals when we're doing calculations. The standard error, which is the standard deviation for the proportion, I have to do the calculation. So I know that p is 0.46. Q is going to be 1 minus the 0.46, which is what, 0.54. Does that add up to 100%? Yeah, that looks right. And then I need n, which is 128. So for the standard deviation or the standard error, I would call that sigma with a little p. That would be 0.46 times 0.54 and divide by the 128. And all of that is inside a square root. So depending on your calculator, you may need parentheses around that. All right, so let's try it on a calculator. And then I'll have to get to 19 next time, I think, unless anybody wants to hang out a little longer. That's 0.46. Ooh, it'll let me type it in. Oh, that's cool. So I could just click the square root button and say 0.46, because it says I can enter an expression times 0.54 divided by 128. So that's one way I could enter my answer. Or I could go over to my calculator and actually calculate that value. What is the square root? Google started my parentheses, 0.46 times 0.54 divided by 128. Just missed a digit. Close parentheses. I think I got that right. 0.44. I think I'll go like 5 places here. 0.04405. So let's delete this. So that should be acceptable too. I typed that right? I think so. Yeah, so that's acceptable too. If I try to enter too few decimal places, the computer might be like, I don't like it even likes that. And then that's my 3 tries, so I'm done. Yeah, so it wasn't too picky on rounding here. All right, Gideon, should we do number 19? Are you still with me here? G3 is still there.
Sure, I'm good.
Okay, let's move along. So it should probably be a similar one because it's right after this one. Oh, and a probability. Okay. Oh, this is a tough one. Yeah. All right. Let's. Okay. So based on past experience, a bank believes that 9% of the people who receive loans will not make a payment on time. Okay. Will not make payment on time. The bank has recently approved 200 loans. What must be true to be able to approximate the sampling distribution with a normal distribution? Think central limit theorem assumptions. So in the beginning of chapter 7, it talked about when you can use the central limit theorem. And let's write this down. In addition, this is a proportion. So there's kind of like extra things that are applied to a proportion. And here I was just kind of hoping for the central limit theorem rules. And in the beginning of chapter 7, let's actually bring it up here. (7.1). I just want to show you this in the book, and then I'll write down my version, which is pretty similar. Okay, so they talk about what the central limit theorem means here, and then this paragraph here kind of says when you're allowed to use it. And the key about the central limit theorem, the word limit in mathematics usually means as one variable changes, another variable does something predictable, is what limit usually means in math. So in this case, what it means is the sample size gets bigger and bigger and bigger and bigger, then these other variables should kind of settle down. And it says 2 things. If the sample is large enough, then you should find that the mean of the sampling distribution, and I'll remind you what a sampling distribution is later, should be pretty close to the mean of the population, and that the standard deviation of the sampling distribution uses that funky formula I brought up a minute ago. And the question is, what the hell does it mean to be large enough? And what we say there is that the sample size should be at least 30. If that's not the case, then you better be sure the data came from a population that had a normal distribution. The problem is we often don't know that second thing. That relies on repeated sampling of a population where we see normal-ish histograms for the samples over and over and over again. So we usually just go with the sample size has to be at least 30. So that's what we're looking for here. And but I wanted to write a note about that. So new page, the central limit theorem. I'm just going to rewrite those first 2 paragraphs a little more briefly. Central limit theorem says as the sample size increases, then a few things happen. and not in any particular order. The mean of the sampling distribution, and in this case, I'm going to say that a little bit different, the mean of the distribution of sample means. All right, so I go out and I take a ton of different samples and I calculate the mean of each, and then I graph all those sample means. Like maybe I did 100 samples, all of size 35, and I graphed those 100 averages. What would the graph, the histogram look like? Let's see, the mean of the, oh my gosh, I screwed that up. I was supposed to say distribution. The distribution of sample means will get closer to the mean of the population in symbols. We say the mean of the means is approximately the mean of the population. That's supposed to be a mu. Other thing that happens is the distribution should appear more normal. Oops, that's be blue. Meaning it has that symmetric bell shape and it meets those 68, 95, 99.7% rules. Appear more normal. And then the standard deviation, let's call it STD, of the distribution of sample means will be about the standard deviation of the population over the square root of the sample size in words, in symbols. And I don't feel like writing out all those words right now. But that's population, that's sample size, square root. So this is basically what the central limit theorem says for us for means. And there's a similar version for sums and a similar version for proportions. But this is the main one we need to know here. So back here, this problem says, like, why can we use the central limit theorem? And so there's a few reasons. And the main is the sample size is over 30. Size is 30. Now, since this is a proportion, then I have this other slight catch, which I didn't really need you to mention here, but I'm going to bring it up because it is sort of kind of important, that the number of successes has to be bigger than 5 and the number of failures has to be bigger than 5. So let's take a look at what that means here. Here they have 9% will not make payments on time. 9% of 200 is 18 people. And so the other 182 people do make payments on time. So 18 is bigger than 5 and 182 is bigger than 5. So the successes and the failures here are both bigger than 5. So I'm okay there too. But this is the main thing I was looking for. Okay, so that's one of the things about the central limit theorem. What does it mean to have a large enough sample? And usually we say make it bigger than 30. Okay, what are the mean and the standard deviation of this model? And so what are we asking about here? The people who will not make payments on time. All right, so I think I need to write a couple things down here. Screenshot. There we go. Let's grab all of this and add to new page. Okay, so they're telling me that P, which would be the proportion, and it's always a good idea to define your variables to help make sure you're making sense of things. Proportion of people who do not pay on time. So that's what it means in words, and they're saying that is 9%, so 0.09 is 9%. I'm going to need to know Q because they're asking for standard deviation. And so Q here is always 1 minus P. And so 1 minus 0.09 is what? 0.91. And a calculator is always a good double check there. So 9% pay, 91%. So 9% don't pay on time, 91% do. All right. And so the standard deviation, so I would call that sigma with a little p, is going to be the square root of that decimal 0.09 for p times q, which is 0.91, divided by 200. And all of that has to be inside the square root. And so some calculators, you need parentheses there. And they want it accurate to 3 decimal places. And then what's the probability that over 10% of these clients make payments on time? Okay. That over 10%. Okay, so if I think about a graph here, they're saying that the people who don't make payments is 9%, so that goes in the middle. So with a proportion, the P is your middle, your mean, and the spread is whatever that calculation is. So let's do that. And then we'll ask StatKey to help us, calculator. So clear, I want the square root, hit start at the parentheses, 0.09 times 0.91 divided by sample size of 200, close parentheses. So 0.020, if I went to 3 decimal places, I'm gonna go for 4 just for fun, 0.0202. .0202, so about 2%. So 1 standard deviation to the right, maybe that's about here. That would be 9, 10, 11%. And then 2 standard deviations to the right would be about, what, 13%, and so on. And 1 standard deviation to the left would be about 7%. So that would be minus 1s, this would be plus 1s, plus 2s. I don't need many of them. I just need to figure out where the heck 10% lives on my graph. Let's use blue for that. So 10% is right in between here. So right about here is 10%. And they want to know what's the probability that over 10% will not make payments on time. So over 10% would be out here. So that means right tail. Okay, so I just need to figure out what that what group of this 200 would fall into that range there, or what group, yeah, it's close to what that means. So now I need a calculator, so either a spreadsheet or StatKey. StatKey is way easier. So StatKey, edit parameters, so my mean is now 0.09. It's got to be the decimal version. And standard deviation is 0.0202. I'm going to go with the 4 decimal point version. And then I need to identify a right tail for 10%. So 0. So 10% is my X value, and it looks like there's a 31% chance that 10% or more won't make their payment on time in a random group of 200 loan recipients. Okay, so back to my picture, and then we'll plug all that in. So we get the probability that the proportion who don't pay, and that's a little p, unfortunately, let's call it p prime, is more than 10%, is about 0.310, according to StatKey. All right, let's see how we did. So should you make the sketch? I think it's helpful in trying to figure out what the hell is going on. You got to make those calculations, and you should write down what you mean when you do them. So the mean was the 0.09. The standard deviation, 3 decimal places, is 0.02, and an extra 0 doesn't matter. And then what's the probability? In this case, there's no percent symbol, so I must want the 0.310. The extra 0 doesn't matter. Hooray. Oh, shit, I got that wrong. Damn. Okay, what did I screw up? What is the probability that over 10% of these clients will not make timely payments? Okay, so 9% of the people who receive loans will not make timely payments. Okay, so make payments on time. So that seems to say the same thing this says. What is the probability that over 10% of these clients, so they say 9% is what they expect, but it could be more or less than that, right? Every situation is different. That's just kind of based on historical data. And then we look at a group of 200 people. I have the mean right, I have the standard deviation right. Did I screw up there? Maybe I typed something wrong here. 0.09, 0.020, maybe it's that extra 2 there. All right, let's pull that out. Maybe getting too close is the problem. See if that differs any. But I think I did everything right otherwise. 0.1 is 10% for my bottom cutoff. Okay, I got a slightly different answer. Maybe that's the problem. So it wanted me to round more. No, well, shit, oh dear. Okay. What is that? Am I misreading that? Does anybody want to chime in and say what I'm screwing up here? I was making videos yesterday and I had to do one video over 3 times because I kept making silly mistakes. What is the probability that over 10% of these clients will not make timely payments? Is it looking for 90 that aren't paying on time? The 90% that aren't paying on time, but 90% are paying on time, right? Because this says 10% of the clients will not make timely payments. This says 9% of people who receive loans will not make payments on time. No, I don't think it's the other 90% we're asking about here. Well, I'm going to get it wrong one more time so it'll show me the answer because I'm at a loss. What is the probability that over 10% of these clients will, over 10%, right? 10% or more. That's what I drew in my picture, right? 10% or more, over 10% will not make payments on time. No, that looks right to me. Okay, what am I screwing up? I had plenty of coffee today. I had my oatmeal. All right, so I'm going to put the 3-1 back in, and then it will show me the answer because that's my 3rd try. And it says 3.311. Huh. Interesting. So the first time, okay, so I'm going to try this just for fun. It could be this 3 decimal place thing here is what's screwing shit up. So let's grab a whole bunch of decimals like this. Remember I said I do that sometimes? I grab like all the decimals the calculator gives me and stick them into stat key. I don't know if stat key will remember them all. It only seems to display a few. Oh, it displayed them all, okay. And then right tail, 0.1. There's the 0.311. Okay, so I wonder if I wrote this problem or somebody else did. I am going to message myself about this. I think STD. Okay.
I think
when I get this message,
kinda,
tell me who wrote it. So,
I think that kind of happened on another problem.
Yeah.
Where it said round to 4 decimal places, but stat key only gives you 3.
Yes. Okay. So when that, if you think you're doing okay, and it looks like, you know, what the hell? I thought I did that right. Hit message your instructor so that way I can look into it. Because I don't. If you spend 20 minutes on one problem, that's probably too long. Let's see. Oh, I forgot to send it to somebody. Let's send it to me. All right. So this will remind me to take a look at it and fix it. Yeah. So if you do struggle with one of these questions, then message me. if you think you're doing it right. And if you could tell me a little about it, if you have any kind of like picture you could send from your phone about what you might have wrote down, like what you were thinking, that would super help me figure out how to help you. All right, well, that was fun and exciting. So